Question number 1. In the diagram below, a line reflection followed by a rotation maps triangle ABC onto triangle DEF. Now we really have to visually think about what they're telling us. A reflection and a rotation both fall into the realm of rigid motions, meaning congruence transformations. So we can make a little correspondence key just based on the way that triangle ABC and triangle DEF go together in our problem. So A goes with D, B goes with E, C goes with F. From this little chart we can match and mark on our diagram the angles that correspond to each other. They will be congruent, and we can choose a different marking for each pair of angles that are congruent. Similarly, we can go across from each of those congruent angles and mark congruent sides. So now that we've done that, which statement is always true? Well, let's examine what the 4 choices have to say. Well, if we look at choice number 1, BC is congruent to EF. And the way that we've marked our diagram, we can agree that that is true. Choice 2 says AC is congruent to DE. That does not appear to match, so we'll put a little X next to that. Angle A matches with angle F. Nope, not according to our chart. And angle B corresponds or congruent to angle D. Nope, not according to our chart. So the only one that really matches is choice 1. Always true. Geometry is a very visual subject. Rigid motions are a big part of the geometry exam. Number 2, a circle is continuously rotated about its diameter. Which 3-dimensional object will be formed? Will it be a cone, a prism, a sphere, or a cylinder? So we have to envision the 3-dimensional object that will happen when we rotate a circle continuously, like flipping a coin, or actually rotating it on a table. So imagine that we rotate a coin on a table about its diameter, the rotation axis. So continuously rotated, imagine the coin is rotating in 3-dimensional space. What is it forming? If you guessed a sphere, you are correct. What about those other choices? What kind of object would have to spin to give us a cone? That would have to be a triangle. Choice 2 just says generally a prism, so we might not be sure about exactly what they mean by that. And choice 4, a cylinder can be found by spinning a rectangle about one of its sides. So choice 3 was our answer here, a sphere. Number 3, in the diagram below, triangle CER, LA is parallel to CR, and I've highlighted those parallel parts here. Now there's a little bit of a typo here, so we'll have to make a change in just a moment, but we have a pair of parallel lines which always indicates some congruent corresponding angles. So we might take advantage of that and mark them in our diagram here. You can think of corresponding angles as the angles that would overlap if you matched the parallel lines on top of each other. Now the little typo we have to make here change is that CE really should read CL. CL is 3.5, so we'll mark that in our diagram. LE is 7.5, EA is 9.5, and we're looking for AR. Now, since it says to the nearest tenth, that's a good indication that we'll use a calculator in this problem. And because of those parallel lines, we're thinking about the side splitter theorem. A side splitter theorem is a proportionality theorem, so start setting up a proportion. The two sides on the left, or parts, are proportional to the two parts on the right. And a proportion is always solved by cross multiplication. So 7.5x is equal to 9.5 times 3.5. Again, you'll probably want your calculator for this. Multiplying the right-hand side out, we get 33.25 is equal to 7.5x. And if your algebra teacher did any good kind of job there, you know that you have to divide by 7.5 to give you this known number. X is equal to 4.4333, repeating to the nearest tenth. We round that to 4.4, choice number 2. Now, in right triangle ABC, you always expect to see a right angle. And in this case, we're going to be involving trigonometric equations, so the acronym SOHCAHTOA comes to mind. The O stands for opposite, H stands for hypotenuse, and A stands for adjacent, all referring to sides of the triangle in reference to a particular angle. So here we have two different angles to consider, A and C, according to our 4 choices. Now, across from angle A, we can mark that as side A, across from angle C is side C, and across from angle B is side B, using lowercase for the sides. Now, if I were to write out the ratio for the sine of angle A, which is the opposite of our hypotenuse, I would write it as side A over B. Similarly, for cosine, I would write that as the adjacent over the hypotenuse, which is side C over B. Now, from the perspective of angle C, we could write out the sine and cosine for them. Opposite over adjacent for sine would be C over B, and the adjacent over hypotenuse for cosine would be A over B. And we notice that the sine of A is equal to the cosine of C, or the cosine of A is equal to the sine of C. So choice A, or choice 1, is the correct choice here, a popular question amongst multiple choice. Now in number 5, the diagram of triangle ABC below has AE bisects the angle BAC. So let's mark out where angle BAC is and mark that it bisects it, which really means that it cuts it into 2 equal angles. It cuts it in half. So we're going to mark those 2 angles as congruent with our choice of, here I'm just going to do a little arc with a hash mark in it. So those 2 angles are equal, and then the altitude is always going to be perpendicular to the side it meets, so I'll make some right angles in there at point D. There's a few angle measurements we can add to our diagram. Angle C is 50 degrees, and angle ABC is 60 degrees, but careful because that takes up that entire angle, which we might just call angle B. So in this problem, there's multiple triangles which we will want to separate out of the picture in order to see what's really going on. And the angle we're looking for is the one FEB. Okay, so I think now first we'll take a look at the whole triangle ABC and put the angles 50 degrees and 60 degrees in there. That'll allow us to find the third angle because we know the 3 angles inside of a triangle must always add up to 180 degrees. So if we take X as our missing angle, plus 60 plus 50 will definitely add up to 180, we get that missing angle to be 70 degrees. So let's pop that in there. But also note that we'll be splitting that angle directly in half. So what is 70 divided by 2? It's 35 degrees. So really, let's put the 35 degrees into our picture here, and now we can examine a different triangle using some of the angles that we know. Namely, let's look at triangle ABE. So we have a 60 and a 60 and a 35 degree angle, and the missing angle in there is the one that we're really after, angle FEB. So by taking the 2 angles and adding them up to 95 degrees, subtracting that away from, again, 180 degrees, we get the missing angle to be 85, or choice 4 in our multiple choice question here. multiple choice questions do involve a little bit of work. Usually it's a layered problem. Expect that. Okay, let's go on to number 6. A jewel company makes copper heart-shaped pendants. So each heart uses 0.75 cubic inches of copper, and there are 0.323 pounds of copper per cubic inch. And if the copper costs $3.68 per pound, what is the cost of 24 of these copper hearts? So one heart has a volume of 0.75 cubic inches. And so we look at the other number there and check out that the units are in pounds per cubic inch, or mass over volume. And that makes us think about density. So this is the density of copper. Now, density is equal to mass over volume as a formula, D equals M over V, which could be solved for mass because the cost is, well, it's in terms of mass. So how do we find the mass of something? We're going to solve it by multiplying the density times the volume. Okay, so the geometry part of this is the volume part of this. So we have the volume of one heart, but we need the volume of 24 hearts. Then we need to know the mass of those 24 hearts, and then the cost of those per pound. So now, laying out our problem, we kind of get a sense of what we have and what we want. So we really want the total cost of 24 copper hearts. So whatever one of them is, we can just multiply the end result by 24. So first, the mass of one heart is found by doing the density times the volume. 0.323 pounds per cubic inch times 0.75 cubic inches. We get the cubic inches units to cancel out, leaving us with pounds, the weight of one heart, and that's what we expect to have for the mass of one heart. The number comes out to be 0.24225 pounds, a small fraction of a pound, the weight of one heart. Okay, so that's the weight of one heart. We want the weight of 24 hearts. So we'll just take this value, multiply it in our calculator by 24. And that gives us 5.814 pounds for 24 of those hearts. The weight of 24 hearts. Now, since we know the weight and mass for the 24 hearts, we can now multiply that by the cost per pound, which is $3.68 for every pound, and we have 5.814 pounds. So together, if you look, the multiplication of the pounds units will cancel, leaving us with a dollar amount of how much all of those will cost, and we get $21. And, well, since this is money, we'll have to round to the nearest cent. $21.40 is the total for 24 copper hearts. That's going to be choice 2 in our multiple choice selection here. Look at the amount of work that a multiple choice question requires so that you are prepared to bring this to the exam yourself. Okay, now we're at number 6. Next is on to number 7, another right triangle problem. Here, right triangle LMN, where M is the 90-degree angle, and 2 of the sides are given. Now, if 2 of the sides are given, this begs for the Pythagorean theorem to find that third side, but here they're asking for the cosine, so this is also a SOHCAHTOA problem, a trigonometric ratios problem. To find the cosine, we need the hypotenuse, and again, we're going to use the Pythagorean theorem. This old chestnut is x squared equals 12 squared plus 16 squared, or 144 plus 256. X squared is equal to 400, and taking the square root of both sides, we get x is equal to 20. So now we have the 3 sides of the right triangle, and we can write the ratio for the cosine, the adjacent over the hypotenuse, which here is 12 over 20. Choice 1. Expect a question like this on your exam. Moving right along. In triangle ABC below, DE is drawn such that D and E are on AB and AC respectively. If DE is parallel to BC, which equation will be true? So here I'm putting in my corresponding angles that are congruent based on the parallel lines. And what I want to do is I want to pull apart the overlapping triangles, split it up so that I can look at them respectively as separate triangles. Now if I try to look at, after I've set them up in a corresponding way, so I know like which sides match, which angles match, and they're proportional by angle, I can now see if the four choices match in a corresponding way visually. So for choice 1, I'm going to locate where AD is and DE, so it's the two sides of that triangle. And then, well, wait a minute, DB is not even a side of a triangle, so therefore that's not the first choice. Alright, so then we look at number 2. AD and DE, again, are these two sides of the little triangle. AB and BC, yes, that's the one I wanted to write down originally. That's the one that is true. So we have that works. Those two things match in a corresponding way. So that looks like a good candidate for my answer. But exploring the other ones, looking at where those correspond, so we have the left side of that one and the bottom of the other one. Yeah, that doesn't seem to correspond in any matching way. And again, for number 4, choice 4, again, that does not match in any kind of corresponding way. So therefore, those are not really good choices. Those could be thrown out as, choices. If you want to eliminate 2 out of there, those would be good choices. So now the next one, number 9, says, which polygon does not always have a congruent diagonal? Let's explore each one visually. So choice 1 is a square, and if I draw its diagonals, it should be obvious that they are the same length. So squares have congruent diagonals. That's not the one I want. Similarly for a rectangle, even though a rectangle doesn't have all 4 sides equal, its diagonals are in fact equal. So it's not the one I want. Now a rhombus is just like a parallelogram with 4 equal sides. And when I draw in the diagonals here, they don't appear to be the same length. There looks to be a longer and a shorter one. So it doesn't appear that the diagonals are congruent in this one, so that looks like it's probably my answer. But I must consider all 4 cases. So number 4, the isosceles trapezoid. The 2 non-parallel sides being equal, well, if I draw in the diagonals, they do look equal. In fact, it's like looking at the rectangle from a perspective from far away. So actually, that is not an answer. So number 3 must be the choice I'm looking for. Now, in number 10, the circumference of a standard lacrosse ball is 19.9 centimeters. What is the volume of this ball to the nearest cubic centimeter? So diagramming out a ball as a sphere of radius r, we first think about the circumference like its perimeter, and that could be given by circumference equals pi times diameter or 2 pi r. Here we'll use 2 pi r. Now what that's going to allow us to do, since we know the circumference, is allows us to solve for what r, our radius, will be. But we also have to remind ourselves that we need to find the volume of this ball to the nearest cubic centimeter. So this volume of a sphere is given on the reference sheet here as 4 pi r cubed over 3. So what I need to do is I need to take 19.9 equals 2 pi r, solve it for r. Now once I have r, I can plug that into the formula for the volume of a sphere. So r approximately 3.167. So we're going to plug that in here, and we're going to cube that, not square it, cube it, and multiply it by 4 pi and divide by 3. And the answer our calculator here will give us, to the nearest cubic centimeter, to the nearest whole number, is 133. Choice 2. Number 11. Which polygon has a minimum rotation of 180 degrees about its center to carry it onto itself? Now we're going to show here that choice 1 is the correct answer by showing that choices 2, 3, and 4 cannot be. If I take a square, the minimum rotation I need to do so that the square looks exactly identical to it did before is 90 degrees. So that's not a minimum rotation of 180. The isosceles trapezoid. Now, the only way that I'm going to get that to look the same is if I rotate it 360 degrees. So that is not a good option. Now the regular pentagon, since it has 5 corners, 5 angles, dividing 360 by 5 gives us 72 degrees. So if I rotate this just 72 degrees, I get the pentagon to look exactly the same. So the only one that has a minimum rotation will only look the same by doing 180 degrees is a rectangle. Another way to say that is upside down looks just right for the rectangle. In number 12, circle O is drawn below with a secant BCD, and the length of tangent AD is 24, so I'm marking where the tangent is. It just means it touches the circle. Secant will go through the circle, so the secant will have both an outside part and an inside part of that segment. And we will consider the outside part called O, and the whole part I'll call W. So now the ratio of the inside part and the outside part, or rather I should say, the outside part to the inside part, is a ratio of 4 to 5. We could use this algebraically as 4x to 5x. So 4x and 5x will represent the lengths of those two parts of the segment. Now, from circle geometry, these segment pieces are connected in the following formula. The tangent squared is equal to the outside part of the secant multiplied by the whole part of the secant, or as I like to call it, the toe formula. So we're going to need the tangent squared, which is 24 squared, equals. The outside part is CD, so from our ratio, CD is going to be 4x. We'll replace that in a moment. And then the BC part is the inside part, or shall I say BD, is the whole part that we need. So we need W to be BD. So BD is a combination of the inside part and the outside part, so BD would have to be replaced with 9x. So 4x times 9x is 36x squared. So equating the left and the right hand side of this, 576 is equal to 36x squared. Now dividing out both sides by 36, we're going to get 16 equals x squared. Taking the square root of both sides, we get x equals 4. So that's our answer, right? Well, not so fast. You see, we need the length of CB, so choice number 4 equal to 4 is what we call a distractor. We really need the inside part, which is CB, or BC, and that's given by 5 times x. So since x is 4, 5 times 4 gives us 20. And that's choice 2. That's the one we really want. So be careful of those distractors. Number 13 says the equation of a line is 3x minus 5y equals 8. All lines perpendicular to this must have what kind of slope? Well, first, to get the idea of what the slope of the line that they gave us is, it might be better to put that line in what we call slope-intercept form, or as you might know it, y equals mx plus b. And then once we know the slope of that, perpendicular slopes are always the negative reciprocal of that original slope. So, putting our original equation into y equals mx plus b so we can locate what m is, we're going to first I would go through this as a student, I would maybe try to get y by itself by subtracting 3x to the other side, leaving us with negative 5y equals negative 3x plus 8. Then, dividing by negative 5 on both sides, we would get y equals negative 3 divided by negative 5 is positive 3/5 x minus 8 divided by 5, or minus 8/5. Now what I care about is the slope, the number in front of x, which is 3/5. And then I need to care about what is this negative reciprocal of this slope. So that would be our perpendicular slope, and here if I flip it and change its sign, it's negative 5/3. So choice 4 is the one I'm looking for. That is our perpendicular slope. Number 14 is a tricky one. The coordinates of the center and the length of the radius of a circle given in an equation in this form must be treated with something called completing the square. So this process starts by looking at all the variables in this. There's x's and y's, and separating out the x's together and the y's together, grouping them together. So one thing we also want to do is leave a little space after our grouping to add a number. So here I have x squared plus 2x, and I'm going to leave a little space to add a number. Then grouping the y's, I get y squared minus 16y, leaving a space for a number. And then finally, I'm going to bring that constant number 49 to the other side of the equation. Here I subtract it to the other side of the equation. Alright, so we move that to the other side, that constant. That's the first setup for completing the square. Now next is going to be deciding what are those two missing numbers. So those are going to be found by looking at the term next to it. Here, for x, we're going to look at the 2 in 2x. That number is always halved, or divided by 2, and then squared. So half of 2 is 1, 1 squared is 1, and that's the number I'm going to add in there. But I must also add it to the other side of the equation to balance the equation. For our y grouping, I'm going to take that negative 16 and half of that and square it. So that's going to be negative 8 squared, or 64. So adding 64 in that missing spot, I must also do to the right side to balance the equation. Now the whole purpose of doing that is that the new groupings that we have, the x squared plus 2x plus 1 and the y squared minus 16y plus 64, and on the other side we get a nice 16 on that side, these groupings can be rewritten in a nicer way as perfect binomials squared, and we'll notice that the right hand side could also be written as a perfect square. So the x grouping can be written as x plus 1 squared, and the y grouping as y minus 8 squared. And take a look at what we did earlier to see where that comes from. 16 is 4 squared, and now we relate this to the equation of a circle with a center of hk and a radius of r. X minus h squared plus y minus k squared equals r squared. And relating the hk to the formula in the numbers that we got in our equation, we can find both the center and the radius of our circle. So the radius is 4, and our center will be here, negative 1, 8. It's negative 1 because there was a sign change from our formula in h to a plus 1 in our equation. Choice 2 is the right answer. But a lot of distractors here, be careful. Number 15 in the diagram below, a right triangle MDL with altitude DG drawn to its hypotenuse ML. A lot to unpack there. Noting that in a right triangle, D is the right angle and hypotenuse is ML, highlighted in blue here. We have an altitude in green here, and that altitude will be perpendicular to the side it meets. Now we have a few things in here, but what we're really looking at are a pair, or rather 3, similar right triangles. The big right triangle and the 2 inner right triangles. Now when we mark out the little pieces of information that we know, MG and GL, and we're trying to find the length of this altitude, it reminds us of something that's called the altitude rule for similar right triangles, and it has something to do with something called the geometric mean, or mean proportional. So the altitude that we're looking for is shared by the 2 inner right triangles, and so you can see there's sort of an L pattern inside those two triangles, which are going to help us set up the proportion. So the two shared sides x are going to go one on top and one on the bottom, diagonally across from each other in the proportion. The other two components are going to fill in the missing spots. From this, we cross multiply and get x squared equals 72, which solves by taking the square root, and that gives us x equals the square root of 72. So that's DG and choice 4. The altitude rule, a handy one to know. For number 16, segment AB is perpendicular bisector of segment CD at point M. To decide which is always true, we really need to diagram this picture out. So I'm going to imagine two segments. One of them is going to cut the other one in half. That's the bisector part. And when it does that, it's going to do it at a right angle, 90-degree angle. That's the perpendicular part. So I imagine first that AB, the thing that's doing the cutting, my knife, is line segment in blue here, AB. So again, this segment is the one that is doing the cutting, so we can think of this as the knife. Now a knife doesn't cut itself in half, but it cuts something else. Here, CD, like a loaf of bread, this is being cut in half, so we don't know that the knife and the loaf of bread are the same length, so we assume that these two segments might be different lengths, but we know that CD is going to be cut in half at a 90-degree angle, because that's what perpendicular bisector means. So I will mark my diagram that it's cutting this segment in half at point M, and it does so at a 90-degree angle, which is the perpendicular part. So that's why it looks completely vertical and the other one is perfectly horizontal. Now our choices involve segments BC and BD here, so I'll put them in there. And we can make an argument that the two triangles that I've created here are congruent to each other by side angle side. So we can state that the two new segments that I added to the picture are congruent to each other. So choice 1 is the one we're looking for. But again, I made this argument because the two triangles in the picture were congruent by side angle side. A tricky thing to maybe see if you don't diagram this out. In number 17, the diagram below of circle O has segments AC and BC as chords. The measure of angle ACB is 70 degrees shown in the diagram. If OA is 9, which we can mark in our diagram there, what is the area of the shaded sector AOB? Now I noticed that OA, the segment that's worth 9, is a radius, and OB is also a radius. So we can mark OB as 9 as well. Now, angle AOB forms a central angle inside that circle that is connected to the outside arc there. And the inscribed angle of 70 degrees tells us that that outside arc must be double that, which is 140. So the central angle being equal to the arc is 140 as well. That'll become important in our area calculation. So to find the area of a shaded sector, we have to compare it to the area of a full circle. So we need to set up a proportion for this. We need to compare the area of the sector to the area of the entire circle, and that'll be compared to the angle of the sector versus the angle that's formed in a full circle. I think you know what that is. So the area of the sector, we'll let that be x because we don't know what that is. To find the area of a circle, we take its radius, we square it and multiply it by pi. So for the area of this circle, we get 81 pi. We'll put that down for the area of the circle. We know that the angle for the sector here is that central angle of 140 degrees. And in a circle, a full revolution around a circle is 360 degrees. Now that we have this proportion set up, most students will use their calculator to figure it out by cross-multiplying, And most students will enter pi as part of that calculation into their calculator, so it'll return the decimal number of 98.96, etc. But none of the 4 choices are giving us that number, so we might think we made a mistake. But if we notice that all 4 choices are in terms of pi, then we can fix our answer by just simply dividing our answer in our calculator by pi, and we can find out what our answer would be in terms of pi. 31.5 pi. Choice 4. Number 18 says quadrilateral best has diagonals that intersect at D, and which statement would not be sufficient to prove that it's a parallelogram? So let's imagine what it looks like as a parallelogram, BEST, and its diagonals are drawn in here. And because we have 4 choices, we'll make 4 pictures here to use. So which one would not be sufficient? We're going to really look at this visually. Okay, so let's take a look at choice 1 and mark that on one of our diagrams here. So BD is congruent to SD, okay? ED is congruent to TD. That's basically saying that the diagonals bisect each other. And that is a property that could show that this quadrilateral is a parallelogram. We're looking for what won't work. So choice 2 says BE and ST are congruent, ES and TB are congruent. Basically, opposite sides are congruent, another property of parallelograms. So that one is not the one we want. Now number 3 says we have 2 congruent sides that are opposite, and the other 2 sides that are opposite are parallel. I'm not sure about that one, so let's take a look at choice 4, and maybe that'll be the deciding factor. So it says that these 2 sides are parallel, and then these 2 sides are parallel. But if I remember correctly, opposite sides are parallel is the very definition of a parallelogram. So that would be good enough. So the one that's not sufficient is going to be choice 3, and now I think about it, that could be describing a trapezoid. So if it could be a trapezoid, it would not be sufficient to prove it's a parallelogram. One of the trickier multiple choice questions, very symbolic and very visual. Choice 3 is the answer, but really, it wasn't that obvious unless we diagrammed it out. Number 19, the equation of line T is given by 3x minus y equals 6. Line M is the image of line T after a dilation with a scale factor of 1/2 centered at the origin. What is the equation of line M? So I put line T into its familiar y equals mx plus b form. Now, when you dilate a line, especially centered at the origin, to get the equation of the new line, we really have to look at what that's going to kind of play out in. And what I'm going to do here is sketch out an XY graph. Now, here's the origin. And y equals 3x minus 6 has a y-intercept of negative 6 and a positive slope of 3, so it will look something like this. Now, if I'm going to scale factor this by 1/2, I'm going to shrink it down. So I'm really going to have to zoom in on this picture that I drew here. So let me make a bigger version of that over here. Alright, so I have the points here that I plotted, and I'm going to also plot where the x-intercept of our equation is. It's at 2, 0. Our y-intercept is 0, negative 6. Right, so that's kind of making a triangle in this little picture. Now, the 2 coordinates, 2, 0 and 0, negative 6, will be dilated by multiplying each of those numbers by 1/2, or dividing by 2. So that gives us new coordinates 1, 0 and 0, negative 3, and the smaller triangle I can draw with that is our dilated triangle. Now the line that would go through that has a y-intercept of negative 3 and the exact same slope as the line we started with. So y equals 3x minus 3 will be the equation of our new dilated line, and that's going to be given by choice 4 in our multiple choice. That one is a pretty tough one if you do not use the grid provided on the back of the Regents exam. Number 20. Now, a cylindrical pool has a diameter of 16 feet. Diameter goes all the way across the circle. A height of 4 feet. If the pool is filled up so that 1/2 foot is left on top, that means it's really been filled up to 3.5 feet. Now, how much water does the pool contain to the nearest gallon if 1 cubic foot is approximately equal to 7.48 gallons? Well, we'll have to find the volume of this cylinder and then convert the cubic feet into gallons. The volume formula for a cylinder is pi r squared times the height h. And solving for the radius here, half of the diameter, is 8, and 8 squared is 64. So we're going to get 224 pi as the volume, but again, we're going to need our calculator to estimate this in terms of a decimal value, and then convert that into gallons. So right now our volume is about 703.7167544 cubic feet of water. Now, setting up a proportion, 1 cubic foot is to 7.48 gallons, as our number of cubic feet is to x gallons. A lot of proportions in this test. Cross-multiplying gives us a value of x as 5,263.8, which rounds up to 5,264 gallons, or choice number 3. The area of triangle tap is 36 square centimeters. The triangle Joe is formed by connecting the midpoints of the sides of triangle tap. Upon visual inspection, that smaller triangle is exactly 1/4 of the entire triangle. So it would stand to reason that the area of triangle Joe is 1/4 the area of triangle tap. Triangle tap has an area of 36 square centimeters, and 1/4 of that would be 9 square centimeters, or choice 1. Number 22 is a grid, and on it points A and B, and we want to know if this line were dilated by a scale factor of 2 centered at the point 3,5, what are the coordinates of the endpoints? Let's zoom in to get a better perspective on this. The center of dilation is like a light bulb shining on the line segment AB, so we can draw these two light rays coming off the center. Now, using the rise and the run from the center to A, and counting the same thing to the new point, we'll do the same thing for point B, counting the rise and the run to point B from the center, and doing that from B to B prime. Connecting our new 2 points, we have 2 parallel lines, which indicates we did it right. And reading the new coordinates off of our grid, A prime is -9,3, where B prime is 7, -1. That's going to give us choice 4, and that one, you really have to map it out on the grid. Number 23 is a circle problem. AD is given to be parallel to BC, and we have a tangent line, EDF. The 2 chords being parallel gives us a pair of alternate interior angles that are congruent. And at first glance, you might test out these 4 choices and see what they offer. So where's angle ADE? Well, it's right here with the double angles I'm marking, and that's being said to be congruent to this angle CAD. It doesn't appear that those 2 angles are congruent to each other, so we're not going to mark that. We're going to mark that off our list here. How about that second example? Where do those 2 angles live? Well, we have one angle here marked by that double angle. The other one is right here. They don't really appear to be the same angle either. I'm going to cross those off. How about choice 3? They're referring to these 2 angles, BCA and DCA. Doesn't appear that those are going to work either. Well, I guess it's choice 4, right? Well, let's really see. Angle ADC and angle ADE. Let's locate those. Right here. And ADE. Doesn't look like those are congruent either. So what's the deal here? We must have missed something. All right, well, here we have to consider that the arcs of the circles might be involved in the relationship to the angles. So let's take a look at, specifically, let's let arc CD be y degrees. So the measure of angle CDF, that inscribed angle will be y over 2, and DAC will also be an inscribed angle of y over 2. So both of those angles are going to be congruent to each other because they subtend the same arc and are half that arc. All right, so that's looking good for number 2, but wait a minute. Not exactly. Oh, well, wait a minute. So when we also have those alternate interior angles being congruent to each other. So if angle ACB is congruent to angle BCA, which is also equal to y over 2 degrees, then yes, this is our choice. It just wasn't obvious that that was our choice. Sometimes the answer is elusive. And our last problem, number 24. In the diagram below, we have triangle ABC. D and E are midpoints on the sides there, respectively, and that's going to give us parallel lines. So because of those parallel lines, I'm also going to draw in my corresponding congruent angles. I'm also going to split these triangles to view them as separate triangles and see what kind of conclusions I can make. Well, certainly these two triangles are similar by angle. But also, we can sort of look at the fact that there's the side splitter theorem at work here and argue that the sides will be proportional to each other. So side angle side similarity could also hold here, and if that is true, all sides would be similar or proportional to each other in a corresponding way. So side could be argued. But that was something of a contested result. I'll leave it to you to decide. That's the last of our multiple choice questions. I hope this was helpful. Good luck on your exams. If you like this video, please hit the like, subscribe, and notification bell for more videos, and stay tuned.